Log on, tune in, find out. Another good idea from Cambridge.
Today by Uded Regev from Tel Aviv, and the title is on the board.
Thank you, Gideon. Thank you for inviting me here. This is joint work with Boaz Klartag, who is from the math department, Tel Aviv University. He'll actually be here later this semester, I think around June. So this is work motivated by communication complexity, by theoretical computer science, but it's mainly a mathematical statement that we'll get to in a few slides. I'll start with the motivation from computer science. But we won't, so this is just some motivation. We won't need this later on in the mathematical part of the talk. So this is the setting. It's one of the main models in computer science. It's called communication complexity. And in case you haven't seen it before, the setting is the following. So there's some problem that two parties wish to solve. So Alice has some input x and Bob has some input y, and they want to compute some function f of x, y. Now, the limitation is that what we're trying to do is minimize the amount of communication Alice and Bob have to communicate to solve this problem. So this is the model of communication complexity. They kind of transmit over the internet bits from one to another, messages, and the goal is to minimize the amount of communication. Okay, so this is, in case you haven't seen this model is used everywhere in computer science. It looks very simple, but it has applications in many fields in computer science, even related to things like P not equal NP, but circuit complexity. So, and also maybe as another example, one of the famous problems here would be, say, one example would be, say, they want to check equality. They want to check if x equals y. It's a typical question here. A naive thing would be for Alice to send all of her string to Bob, say, that would require n bits of communication, but kind of related to Avi's talk yesterday, it turns out if you use randomness, you can do it much more efficiently. So you can do it using only log n bits of communication from Alice to Bob using randomness. So think about it. It's a good exercise to check if two strings are equal. But that's our topic today. And at the end, say they have to output the value of the function f of x, y. So this is this is the setting that we'll be dealing with today. And there are two central models here. The two models that we'll consider here, there's the classical model, and for us we allow randomization, we allow bounded error communication. This is the standard model in this setting. And there's another model that started around the mid-90s. This is the model of quantum communication. I won't define any of them formally, but you'll see later on where this comes in. And in all of these since the middle 90s, 1990s, people started wondering about the connection between these two models. Are they, is quantum communication really stronger than classical communication? Okay, this started with papers by Burman, Cleve, and Vigdason, Ambanis, Tashma, Schulman, Vazirani, and Vigdason. And there were some examples showing that in certain scenarios, quantum communication can be much stronger than classical communication. And maybe the strongest result in this line of work is by Ranras from 1999. And it's a very nice result. I think it's kind of one of the most fundamental results in this area. Also nice mathematically. It showed that there's a function that if you have quantum communication, you can solve it using only log n bits of communication. Okay, that's very good. But if you don't have quantum communication, if you restrict it using classical lines like the internet, you need much more. You need n to the 1/4 bits of communication to solve it. Okay, so there's this exponential gap between the amount of communication you need to solve the problem. The problem is quite simple. I'll show you later what the problem is. So in other words, what he shows, Raz showed that quantum communication can be exponentially stronger than classical communication. Now that doesn't mean that all problems are exponentially faster with quantum communication. Otherwise we would really have a good reason to build a quantum internet and things like that. It's just that certain problems are much faster, okay? And I think, as I said, this is one of the most fundamental results in this area. So this is a very nice result. And one open question that the question we'll be dealing here with today is one-way communication enough? So you might consider a model where there's just Alice and Bob are restricted to use one-way communication, one-way quantum communication. And the question we're dealing with here today is well, this is still enough. So if you consider Raz's quantum protocol, you see that it only requires log n bits of quantum communication, only log n qubits, but it has to be both way. Alice has to send log n qubits to Bob, and then Bob has to send back log n qubits. So it's only log n, but there must be this kind of both way of communication. And you might ask, is that necessary? Can you do same exponential separation with only log n qubits of one-way communication?
So in one-way communication, if Alice is communicating to Bob, then she can't possibly know the answer at the end.
Right, and then Bob outputs the answer. Yeah, that's yeah.
But
So
are there classical problems where it's proved that that it's possible with two-way and not possible with one-way? That there's a big
yes. So I mean,
complexity gap?
there are examples where classically, yeah, you need two-way to solve problems. It's not difficult. Yeah. Okay. So this is what this is the question that we're trying to address today. Can quantum one-way communication be exponentially stronger than classical communication? Okay, so this is strengthening of as a result, and that's what we'll try to answer today. So I'll just quickly go over previous work. It's just for those of you more familiar with this area. Let me just say the first work is by Bar-Yosef, Jaron, Karanidis. The first result in this area, they showed something slightly weaker. So they showed a separation, but only when the classical parties are also restricted to one-way communication. I don't want to restrict classical parties to one-way communication. I want to show a task that classical parties just cannot solve even with two-way communication. They also have another minor issue there, not so minor, another issue with the function being actually relation, not a function, meaning that there's more than one possible output. This often makes things quite different. This was improved a few years ago by Gavinsky, Kempe, Karanidis, Raz, and DeWolf to a function. So this relation became a function, but still they force the classical players to be one way. So it doesn't quite answer the question because of this quite severe restriction of the classical players to only have one way. I should say the problem the first paper considers quite interesting. It's called the hidden matching problem. It was used in many other results since then. But it's naturally, it's only hard if it's one-way communication. Once you do it in the other direction, it's very easy. That answers your question, Ehud. So if you do this in two-way communication, it's very easy. Okay. And just, more recently, there's a paper by Gavinsky who shows a relational problem that has the properties we need. So it's not a function. It's not really computing a function. It's computing some kind of relation. There's more than one possible output. But at least it gets the right separation. You get quantum one-way communication is exponentially stronger than classical communication. So this is kind of a brief overview of previous work. If you didn't follow all of it, it's okay. And what we do here, we just solve the open question. We show a function with log n, all the log n quantum one-way protocol that requires some n to the epsilon quantum communication classically without any quantum bits. Okay, so there's this exponential separation. If you have quantum communication, you can solve it using just one-way communication, but with classical communication, you need some exponentially more communication. Okay, so this is what we show. Quantum one-way communication can be exponentially stronger than classical communication. So this kind of solves this open question as it's potentially kind of the strongest separation you might hope to prove between quantum communication and classical communication. Questions so far? Okay, so this is so far for motivation. We'll soon get to the mathematical part. Let me just tell you what the problem is. So you see the connection to the mathematical part. It's actually a very natural problem. So Alice has as input a vector, a unit vector in n dimensions. And Bob has as input a subspace of dimension n/2. Okay? And there's a promise, so these inputs are chosen from a certain set, and the promise is that Alice's vector V is either contained in W, so it either lies completely inside the subspace, or it's orthogonal to the subspace. Okay, so V is either in W or orthogonal to W. And they need to decide which is the case. So either V is in W or V is orthogonal to W. How would you solve that?
Inner products with a V with random elements of W.
Oh, but Alice doesn't know W. So you cannot take inner product of V with element of W because you don't know W. So Alice just has V.
Send a vector instead of V.
Oh, Alice is the one who's
Alice
sending.
vector, yeah. Well, no. I mean,
Does it matter who's sending to whom here?
So classically, it doesn't matter.
No, but okay. So in the statement of the problem, what are we doing? This
So
is-
I'll show you, later I'll show you in a minute, actually I can already say it now, I'll show you that there's a way to solve this quantumly using only communication from Alice to Bob and only log n qubits. And this is actually this follows from the first lecture in quantum mechanics, quantum information. The only thing you have to know for that is just the most basic thing in quantum mechanics, that state on k qubits is by definition a unit vector in 2 to the k dimensions. Okay, so if you heard about that, this is exactly what's going on here, because Alice has a unit vector in n dimensions. So to transfer this to Bob, all she has to do is just create the quantum state on log n qubits corresponding to that unit vector. So this is really by definition of the most basic axioms of quantum mechanics. She can send V to Bob, and then this subspace that Bob has, this is also by the axioms, this is just what's known as a quantum measurement. Bob can do a quantum measurement and figure out if V lies inside W or orthogonal to W. The question I'm asking now is, what can you do classically? So you don't have quantum communication, how do you solve it?
So we're done with the quantum model for the rest of this talk?
Yes, so actually this is the only quantum part here. I think it's the result with the least quantum ever accepted to the yearly quantum conference. Yeah, so it's only this part is quantum. And it's mainly classical result about lower bounding the classical communication.
So if it's
Promise problem?
So
Is that okay for you?
Yes.
But-
That's what you promised.
I'll say later about this. So it's a promise problem for the experts.
so how much better? I mean, naive thing is to transfer all of V.
Good, that's what I want to do. So the naive thing would be to send all of V, right? And that would take something like, well, these are real numbers, but you don't need this extremely good precision. Essentially, n log n bits would be enough. So n log n bits are enough. Alice just sends the vector V to within some precision. That's enough, and then Bob can just compute the overlap of V with W.
So does this have to? You just said something about precision. Does this have to be a continuous question? Does it
No,
have a discrete
No,
analog?
it is. You can make it discrete. Yeah, this is just.
You
for
cannot
simplicity.
represent V by a classical probability distribution on log n bits and somehow.
Well, you can try, but the proof shows that you cannot. So, if the proof is correct. So, okay, so here's the. So here's what we said. Let's summarize it. There's an easy log n quantum communication protocol. So all you have to do is just transfer the vector as a quantum state. It requires log n qubits. It's really by definition. And actually, this problem is very natural. It comes up. It's a kind of complete problem for this class of quantum one-way communication. It was defined, I should have said, already 95 by Kremer. And no classical lower bound was known. That was the main open question. That's what we'll show here, classical lower bound. And we'll show this. We'll show lower bound of n to the 1/3. So we showed to solve this problem, you need n to the 1/3 bits of communication, no matter which way. Bob can send things to Alice, Alice sends things to Bob. And I should say, so you actually weren't, your algorithm is not the best. Turns out there's a square root n communication protocol for this. And this is very good exercise in geometry, in high-dimensional geometry. Try to figure it out. You can find this in Raz's paper. So there's a nice protocol solving this with only square root n communication. But it seems like the lower bound is nearly tight. We believe the upper bound is the right answer, but I'll mention more about this later.
And you have to. Are you allowed errors or?
Yeah, so the model is randomized, yes. So you allow some small probability of error. Yeah. Okay.
So what happens if Bob chooses a random basis for a space and starts sending the vectors to Alice and she checks the inner product if they're always zero or if there's something like that?
No, I don't think that
Sending
would
one
work.
vector is already.
Yeah. Okay. Okay. So it's an exercise. Don't solve it now. Okay. So before I go into the mathematical part, let me just say for those who are not familiar with this area, that communication complexity often leads to interesting mathematical questions, and the way it's done is by there's one method this is done. There's a method to translate questions about communication complexity to questions, more mathematical questions about rectangles. I just want to quickly just flash this so you see, so at least you see it once.
Generic rectangle?
This is a generic rectangle, yeah. it's the aspect ratios because of the projector. It's not right. So the way you prove a lower bound on communication complexity, in case you haven't seen this before, you try to understand what it means for a communication protocol, what the communication protocol really does. So if you think about this, this matrix is supposed to represent the rows correspond to all possible inputs by Alice, and the columns corresponds to all possible inputs of Bob. Okay, so imagine it's finite. So what happens in the protocol is first, Alice, so Alice is the columns and Bob is the rows. First, Alice sends a bit to Bob, and that bit partitions Alice's set of inputs into two sets, the set on which Alice sends 0 and the set on which she sends 1. This is why I partition now this matrix into two parts.
So this is deterministic here.
Assume it's deterministic. You use Yau's principle to make it deterministic. The second step, Bob sends a bit based on his input and based on Alice's first bit. Okay. So then we further partition each such thing into two rectangles. So this is Bob's bit, and assume the next step is Alice sends a bit, and then she partitions each such rectangle into two rectangles, and so on and so forth. At the end of the protocol, they agree on an output, either 1 or 0 for each rectangle. So that's what it looks like. And okay, I don't want to make this more precise. I'll just say that once you have this, and once you do the math, it turns out that the equation reduces to a very nice, clean mathematical equation, which I'll describe next. So from now on, there won't be any communication complexity here. You have to believe in this step is done right. But this is often done. You just reduce the equation to an equation about just one such rectangle. It's much nicer to analyze. Okay, this is what we do from now on. So there's a step here. I'm not showing you the step, but it's quite standard. You just have to take my word for it. Okay. So questions so far before we go to the math, more mathematical part. So here's the proof, and this is kind of the demonstration of the proof. You'll see in a minute why. I should maybe apologize. So this is a statement about harmonic analysis. It's not so discrete. You see, I'm dealing with vectors here, but I hope you like it anyway. There's actually some discrete analogs of this, which I mentioned. So here's the proof, and then first maybe I'll start with motivating the mathematical statement that we would like to have, and I brought some props here for this. So this is Earth. And here's the motivation. It comes from the following obvious statement that being on the equator is great, of course, right? We have all this rainforest, we have great fruits, and islands, tropical islands. So far, I imagine we all agree with that. But this is something maybe not all of you have realized, is that only 21.3% of the equator is land. The rest is sea. And this is, okay, you might say, sure, so what? But I claim this is quite unfair. And it's quite unfair because 29.9% of Earth is land. So we lose almost a third of the land here. Okay, we have 29% of land on Earth, but only 21 of it is on the equator. Okay, and this is really not fair, right? This shouldn't be the case. And if you really think what causes this, it's mainly because, like in Europe and Asia being north of the equator, far north, we're doing pretty well, say in Africa, but not so well either. Does anyone know where else all the land goes? Any other guess?
South America.
Israel?
Not Israel, no. no.
Your Mercator projection.
So yeah, so the Antarctica is actually quite big. It's almost as big as South America, and it's really not in the right position for the equator. It's actually so. So this is, I think, this is a serious problem. And actually, you can easily see that had the continents been spread kind of uniformly, you would expect on average 29.9% on the equator, right? You can easily prove it. I mean, any point on the equator should have probability 29.9% of landing on land. So there's really some kind of injustice here, and the question is how can we correct this, and this is what we're trying to analyze here. Of course, you can try all sorts of global warming effects, but there's a more practical solution, and the more practical solution is to change the equator. So we just rotate Earth randomly, and then stop at some point. So rotate, and then we just check. Once we stop, we have a new equator, and we hope that then we'll get something closer to 29.9%. And that's exactly the question we're trying to answer here. That's the question that you have to solve to figure out this communication complexity question. And the question is, so we know the expectation will be 29.9. I told you kind of the proof before. If you do random rotation, the average landmass on the equator is going to be 29.2. But the question is this concentrated? Okay, how well concentrated is this? Because we don't want to end up with suddenly 10%, that would be even worse. So that's the kind of question that we're dealing with here. Let me show you more precisely what we're proving. And this is the equator sampling theorem. So we're showing the following statement that take an arbitrary set of this measure on the sphere in n dimensions. So the measure is exponentially small in, so it's exponentially minus n to the 1/3. Okay, so it can be pretty small, but not smaller than that. Okay. And now what we do, we take a uniform equator. So in other words, we take an n-1 dimensional subspace, a uniform n-1 dimensional subspace. What the theorem says is that the measure that we'll see on that equator, the measure that we'll see of land is a very good approximation of what it should be, of the measure of A, within a multiplicative area of 1 plus minus t. So the area is multiplicative, 1 plus minus t, and the probability of deviating by more than 1 plus minus t is this, is e to the minus t n to the 2/3. So let's just figure out what this means. It means that area is typically 1 plus minus n to the minus 2/3, and it has an exponential tail, right? So plug in t equals n to the minus 2/3, you see there's some constant probability of being in that multiplicative area. And as t grows larger, this decays exponentially. Okay? So there's very nice concentration and around the right measure of A. Okay? You can do it in 3 dimensions. Everything here, n is the dimension, everything else is asymptotic, but you can in principle do everything here in 3 dimensions if you really care about the question about Earth. I haven't tried that. So this is kind of what we need to prove our statement or communication complexity law bound. What I'm saying here is actually this is what we really need. So what I showed you before is a statement for n-1 dimensionally subspaces. What we actually need is a statement for n/2 dimensional subspaces. Okay, this is what really leads to the communication complexity lower bound. So what I try to do now is first show you how to derive this statement from the previous one, and then we'll discuss how to prove the previous one. Okay, so this is the statement that we actually need for the communication complexity lower bound. It says that, again, take an arbitrary subset of the sphere, assume the measure is e to the minus n to the 1/5, as before, not less than that. And now we take a much lower dimensional thing. We take a subset of dimension n/2. And the claim is that we still have good concentration, or more precisely, the error is within plus minus 10%, except with probability that's e to the minus n to the 3rd. Okay. So what I'd like to show you now is how to derive this from the previous statement. So again, what we want to show is that the concentration of plus minus 10%, as the probability is very good. The probability of deviating more than 10% is only e to the minus n to the 1/3. Okay. And this, as I said, this implies what we need. This implies the n to the 1/3 lower bound using a routine application of the rectangle bound. I should also say this and the previous theorem are all tight. You can, if you do this calculation for spherical caps, you see that all the estimates here are tight. So you might wonder how to improve the lower bound to square root n. I'll show you at the end. But the mathematical statements that we have here, they're all tight. Okay, so how do we prove theorem 2 using theorem 1? So theorem 1 tells us what happens when we take n-1 dimensional subspaces, and now we want to go down to n/2 dimensional subspaces. And here's how we do it. So we use some kind of process to then generate that n/2 dimensional subspaces. So you can imagine, one way to generate an n/2 dimensional subspace, uniform one, would be first take a uniform n-1 dimensional subspace. Inside it, take n-2 dimensional subspace, and then n-3, n-1, and after n/2 steps, you get to a uniform n/2 dimensional subspace, right? I guess it's believable, right? And this indeed works. This is what we'll do. And what we want to do now is analyze the way the error accumulates over these n/2 steps. Okay? So we know from theorem 1 that each step gives us a good estimate of the measure of the set. So we start from some set, we take a uniform n-1 dimensional equator, right, a subspace. Inside it, the amount of land is going to be close to what it is in the whole sphere. Okay. Hence, we can continue the argument. We'll take another n-2 dimensional subspace, and again, we use theorem 1 to say that it's a good approximation of the measure of the sphere, and so on. So let's see why this works, or might work. I won't show the whole proof. So, theorem 1 shows that at each step of this process, we get an extra multiplicative error of 1 plus minus n to the minus 2/3. Okay, now we have something like n steps. We have n over 2 steps. So how much error do we accumulate?
N to the 1/3.
Okay, first reaction would be something like, e to the n to the
1/3.
1/3. That's quite bad, right? Exponential. We want a good multiplicative approximation. We want 10%, 1 plus minus 0.1. So luckily this is not as bad. Any idea why?
It's like a random walk. It goes up and
It's
down.
like a random walk, because it's sometimes going to be plus n to the minus 2/3, sometimes going to be minus n to the minus 2/3, and if we're lucky, they're going to cancel out, and if we're very lucky, we're going to end up with this. We're going to end up with that after n over 2 steps, the error only grows by square root n, not by n, okay? Due to cancellations, because it behaves like a random walk. Okay, you actually have to prove this, of course, but indeed that's what happens, and you can prove this. After n over 2 steps, the error becomes 1 plus minus n to the minus 1/6. Okay, so this seems actually even better than what we needed, right? We needed 10%, and now we have 1 plus minus n to the minus 1/6. So how come? How come? How come it's so strong? I mean, this is suspicious. So something, I should say,
With what probability?
with what
does it
probability,
happen?
right? So what I wanted to have is 10% error, but with very good confidence, right? I want the error probability to be e to the minus n to the 1/3. But if I know that the typical error is n to the minus 1/6, and if I also believe that this has some kind of normal distribution, then the probability of deviating by 10%, that's n to the 1/6 standard deviations, that's e to the minus n to the 1/3. Okay? But again, something to prove, something I haven't proven. You need to prove that this really has some kind of normal behavior. So there are things to prove here, and you need to use some martingale argument to actually make all this go through. Okay, so you have to just carefully calculate, you do some kind of Bernstein argument to make sure all the martingale goes through, and you indeed get the right statement. Okay. So that's it for how to derive theorem 2 from theorem 1. Any questions? Okay, so now we can go to discuss theorem 1. And theorem 1 is, just to remind you, so the theorem 1, well, I'll show it again in a minute. Let me just say, theorem 1 is based on the following thing. So you need to use the Radon transform, the spherical harmonics, and the hypercontractive inequality. I'll show you how all these ingredients combine together. And actually, well, the proof is not difficult once you write it in the right language. So you see, it's actually not difficult. I should also say, because this is a workshop about discrete harmonic analysis, that you can actually do everything from now on. Everything I'll say can also be done in the discrete case. You can have exactly the same statement or the analog of this statement in the hypercube in 0, 1 to the n. What it means there is that an equator is just a set of all points of Hamming distance n over 2 from some fixed point. Because that's an equator in the Hamming cube. And the statement says that for any, same thing, for any set of measure 2 to the minus n to the 1/3, sampling it using such equators gives you a good estimate of the measure of the set. Okay, so I'll tell you a few words about the proof of theorem 1.
Can you remind us of the parameters of
Yes,
theorem 1?
I'll write theorem 1 again, and here's theorem 1. Oh. Yeah, okay. I hope I didn't remove that slide. So, yeah, okay. So, yeah, first let me introduce this, and I'll run you the parameters once we get there. Yeah, the next slide. So, the first thing we need to use is something quite natural here, is something called the Radon transform. It's used a lot in applied math. It's used for computer tomography. It's this thing that allows you, based on, say, two-dimensional projections of some distribution, to infer its internal structure. Okay, so this is used, for instance, in the computer tomography. That's some kind of Egyptian mummy going into this machine. This thing also has a natural analog in a sphere, in S(n-1). Usually it's done in Euclidean space, but you can also do it over a sphere. And the way it's defined is the following. So if you take any function on the sphere, the Radon transform is defined the following way. R of f at some point x is simply the average of the function over the equator orthogonal to x. So you see this is very, sounds a lot like what we want to prove. So for instance, if you take the indicator function of Earth and you apply the Radon transform, then the value at the North Pole would be 0.21. Okay, same in the South Pole. Actually, it's always an even function, and you'll see later why. I mean, you'll see later another manifestation of this. So this is the Radon transform, and now we can state our theorem in a slightly cleaner form. Okay, so this is the theorem that we want to prove. I also, for simplicity, I just fix the parameter t to be n to the minus 1/3. Okay, to make our life a bit easier. So here's what we want to prove. There's some subset A of the sphere, arbitrary subset, and the measure is e to the minus n to the 1/3. Okay? And I let f be the indicator of A, except I use this fine normalization, which is very convenient. I just normalize it such that its average is 1. Okay, so I divide by the measure of A, just for convenience. So f is the indicator of A, normalized to have expectation 1, average 1. Now, what we want to say is exactly this. We want to say that after applying the Radon transform, f becomes essentially constant. More precisely, R of f is in 1 plus minus n to the minus 1/3, except for a tiny fraction of x's, except for e to the minus n to the 1/3 of x's. Okay, so it's essentially a constant function. You apply R of f, and at any point, the average on the equator orthogonal to that point is essentially 1 plus minus n to the minus 1/3. Okay. So that's just an equivalent way to write theorem 1. So you see it slowly gets a nicer analytical form, and that will, let's make it even nicer in the next step. Instead of talking about the deviation of this function, let's add some kind of test set where we'll test this function R of f. So I claim that the following is equivalent. I claim that for any sets A and B of measure e to the minus n to the 1/3, the inner product of g and R of f, which is defined as just the expectation over x of gx times Rf of x, this is within 1 plus minus n to the minus 1/3. Okay, so, and again, f and g are just the indicator functions of A and B normalized properly, normalized to have expectation 1. So why is that? I mean, you see that, say, for instance, if the function deviates from this range in more than e to the minus n to the 1/3 of x's, we can take B to be that set where the function deviates a lot, and then its inner product will be bigger than 1 plus n to the minus 1/3. So the statement, these two things are essentially equivalent. Okay. Good. So this is what we want to prove from now on. This is a much nicer, much more symmetric statement. We have just two sets, A and B on the sphere of this measure, e to the minus n to the 1/3. Okay, and we want to analyze the inner product of their indicator functions through this Radon transform. And we want to show it very close to 1. Okay. So how do we do that? So here's the second tool. We'll use spherical harmonics. And this is a very basic tool, but I should maybe say that if you're not familiar with it, you can think of it as just being the Fourier transform or the analog of the Fourier transform in the sphere. Many things are kind of nicer in spherical harmonics, but also many things become dirtier. But kind of it's the same. In principle, it's the same idea. So I'll just give just a very briefly demonstrate what the spherical harmonics are. So what we do, we decompose, say, the set of all functions on the sphere. We decompose it into orthogonal subspaces. So we decompose L2 of the sphere into orthogonal subspaces. We call them Sk, and they're known as the spherical harmonics of level k. So what are they? So for instance, level 0 just contains all the constant functions. So it's a one-dimensional subspace, and this corresponds to in the Fourier language, this corresponds to the empty coefficient, corresponds to the constant function. So this looks very familiar. Also, level 1 is very similar to what we see in the hypercube. Level 1 contains all the linear functions, for instance, x1s, and the subset of dimension n. Just like in the hypercube, we have the level 1 Fourier characters, they span n-dimensional subspace. So this is a subspace spanned by the level 1 Fourier characters. So, and for instance, one function x1, so for instance, function, let's say 1 in the north pole, minus 1 in the south pole, and 0 in the equator. This is like a linear function, and of course you can do it in any rotation that you wish. These are all linear functions. And level 2, you already see some difference from the Fourier case, from the hypercube case. The dimension is a bit different. It's not n choose 2 anymore. It's n squared plus n minus 2 over 2. It's not a difficult calculation. If you've seen this before, it's not difficult. And for instance, you have this element in there, this function x1 squared minus 1 over n. So it's a function whose value is let's say, 1 minus 1 over n in the north pole, also in the south pole, and at the equator it's minus 1 over n. So it's a bit cold in the equator and warm on both poles. This is the animation of this. Okay, but the bottom line is this. Any function can be decomposed into levels. That's what we do in Fourier analysis. You can write any f as f0 plus f1 plus f2 in this decomposition, and then the inner product of f and g is simply by level, right? Because these are orthogonal levels, orthogonal subspaces. So inner product of two functions is simply the inner product in the 0th level, in the first level, in the second level, and so on.
How many values on that?
So that's the nice thing about spherical harmonics, that is actually there's k all the way to infinity.
It's like Fourier series.
It's because we in a continuous setting here, there's infinite number of levels, and that makes some things cleaner, but also some other things not as nice. There's no limit on k. Okay, so why are we interested in this? Turns out there's a very nice connection between the spherical harmonics and the Radon transform. And those of you who've seen things like that before will not be surprised. And this is because the Radon transform commutes with the rotations, and the spherical harmonics are the irreducible representations of SOM. So there's some group theoretic reason for representation theoretic reason for why this happens, but you can also just do it, just compute and see that this happens. So what I want to show you is that the subspaces Sk are eigenspaces of the Radon transform. In other words, the Radon transform just multiplies each subspace by an eigenvalue. So let's just see in the demonstration why this is the case. Let's start saying with the S0, with the constant function. So if I have a constant function 1 in the sphere, and I apply the Radon transform, it's still the same function, right? If I have a constant function, say constant 1 function, at any point the average of the equator is still 1. So it's an eigenvector, it's an eigenfunction with eigenvalue 1.
So that's a hyphen and not a minus at the beginning of the...
That's a hyphen. Yeah, that's a hyphen. Thanks. You can see it's a bit longer than the minus.
Right.
Yeah. So lambda 0 is 1. Yeah. And lambda 1 is 0. That's because of the even symmetry of the Radon transform. Take, for instance, the function x1, function that's 1 in the north pole, minus 1 in the south pole, and 0 in the equator. If you think about this linear function, you see that the average over any equator is 0. Okay, so say the equator is just all 0. But take something like that, you see, part is positive, part is negative, and it cancels, so the average is 0. So this is why lambda 1 is 0. Okay, this is, you can see this also indirectly by just saying that the Radon transform is always an even function, hence all the odd levels must be 0. Lambda 2 is slightly more interesting. Do the same calculation. It's actually, to do the calculation requires a bit of effort, but you can see it's roughly minus 1 over n. In this case, because take the function x squared minus 1 over n, and if you remember, the value here is roughly 1, the value in the equator is roughly minus 1 over n, so that's what you get. The average on the Radon transform in the north pole would be minus 1 over n, so it goes from 1 to minus 1 over n, hence this is the eigenvalue. So it gets a bit messier, you have to do the calculation, so integral, you compute it, this is what you get. The only thing to notice, the only important thing, is there's a very strong decay. Okay, you see 1 minus 1 over n, 1 over n squared. These are not exactly the right values, but there's this very strong decay of the eigenvalues. And this is what gives the Radon transform its smoothing behavior. Okay? And had all these things been 0, except lambda 0, we just get the average. We get a constant function no matter what we put in the transform. But because these are so small, we get something that's very close to, very highly smoothing, very close to constant. This is what we want to make use of. So if we take any function f, apply the Redon transform, what we just showed is that r of f is f of 0 minus 1 over n f2 plus 1 over n squared f4 and so on. Okay, so you see, all the higher spherical harmonics get attenuated by a lot, and we'd like to use this. So let's just write again what we want to prove. We want to prove that the inner product of r of f and g, and now we can just break this into spherical harmonics. It's f of 0 inner product g of 0 minus 1 over n f of 2 inner product g of 2, and so on. This is essentially 1. This is within n to the minus 1/3 of 1. Okay, this is our goal. Okay. So the first term, f of 0 g over, this is easily seen to be 1 because that's the way I normalize things, right? F has average 1, hence f of 0 is simply the constant 1 function, and g of 0 is also the constant 1 function. The inner product is 1. Okay, so this is easy. And for this term, what we'll apply the Cauchy-Schwarz inequality, and we can upper bound the absolute value of the second term by 1 over n, L2 norm of f2 times L2 norm of g2. And we'll do the same for the third term. Okay, so you see what we are actually left with proving is the following statement. So the first term is 1, so we just want to prove that the second terms and the others don't contribute too much. And what I show you is this. I show you that the L2 norm of f2 is at most n to the 1/3. Okay, so this is our goal. Okay, you can do the same for f4, and believe me that the important term is, say, the second term. The others don't contribute too much. We also do the same thing for g. This is for f. The same thing will hold for g because f and g are totally symmetric. Both are indicator functions of sets of the same measure. So it's totally symmetric. So now the question reduces to a very basic question of just bounding the mass of a certain indicator function in spherical harmonic levels of the spherical harmonics. Just bounding the L2 mass in spherical harmonics. I should say, again, everything I've done so far you can also do in the hypercube, okay, as I've mentioned before. Okay. And this is what we actually show. So we show that take any set A of arbitrary measure, take f to be this normalized indicator function. We show that the highest mass of f in the in the kth level is this. Is at most log 1 over the measure to the power k over 2. Okay, this is what I want to show you. And actually, I should say bounds like this have appeared before. This is okay. I'll mention this also later, but this is you can find this in Talleyrand. Talleyrand has this in one of his papers. You can find this exactly. This was used more recently in the paper by Gawinski, that I mentioned earlier, for the hypercube. But I should say all the previous papers that did it for the hypercube. Here I'm doing it for the sphere. The proof is exactly the same. You'll see in a minute. But you just have to work with spherical harmonics instead of the Fourier transform. So, and use a slightly different inequality. I'll show you this in a minute. So what we want to do is we want to prove this. We want to bound the mass in a certain level of indicator function. Okay. So let's just, even though we don't really have to do that, let's just for convenience switch by duality, switch to the following formulation. Instead of talking about the mass a function has in level, let's talk about the tails of polynomials of a certain degree. This is essentially equivalent by duality. So let's take what I claim is that the following would be sufficient. It's actually essentially equivalent. Take p to be any polynomial of level k of the spherical harmonics. Take any function in the level k spherical harmonics, and normalize it such that its L2 norm is 1. I claim that it must have the following tail behavior. The probability that it's bigger than t is at most e to the minus t to the n over k. So it's some kind of tail behavior of polynomials in the spherical harmonics.
Said e to the minus e to the n over here or t to 2?
So say again, e to the minus t to the 2 over k.
2.
Yeah, it's okay. It's written. And just to see, to see the connection, why these two things are, why it's sufficient, we want to upper bound the L2 norm of fk. You can express this as the inner product of fk with itself divided by the L2 norm of fk, right? And now the inner product of fk with fk is just the inner product of f with fk, because it's only the case level that matters anyway when you take inner product with fk. And this is by definition, f is indicator function, so this is by definition the expectation over a of fk divided by L to norm of fk. And this is a function in the case level of the spherical harmonics normalized to have L to norm 1. So you can just apply the statement, and you know it has such a tail behavior, hence its expectation over a small set, hence its L to norm cannot be bigger than that, okay, because of this tail behavior.
When you say probability of x, you mean probability of x uniform in A.
No. So here, that's the thing. So here there's no A anymore. I kind of swallowed the A into this tail bound. So there's no A anymore. It's really probability over all x in the sphere that the polynomial differs by more than t. Let me just give an example. I think it will help. The example is k equals 1. Here it's easy. Here we all know this already. Take linear functions. Take function like x1, function x1 in the sphere. Okay? And if you take this function, you see that the tail behavior is essentially like a normal variable. You know that each coordinate of a vector chosen from the sphere has essentially a normal behavior. So the decay of this coordinate, decay of this function behaves like Gaussian. It behaves like e to the minus t squared. So this is the case of linear function. It's very easy because we understand all these functions. The question, how do we do that for other functions of higher degree in the spherical harmonics? Okay, so if you didn't follow this proof of sufficiency, you can ignore it. Just believe in that's what we need to prove. That if you take any function in the level k spherical harmonics over the whole sphere, there's no A anymore, over the whole sphere, the probability that it deviates, that is bigger than t, is e to the minus t to the 2 over k. So it's some kind of tail estimate for functions, low degree polynomials. So how does one prove such things? And the standard way to prove such things is using hypercontractive inequality, and this is also the way this was proven for the hypercube. So let me just briefly show you how, and then I'll show you how it all combines. So what we want to prove is the hypercontractive inequality. This, when proving things on the hypercube, we all know the hypercontractive inequality, but turns out there's also hypercontractive inequality for the sphere and for much more general settings. In the case of the sphere, this falls for quite general statements by Bucky and Emery, you can also get the right constants using a result by Rothaus, who found the right constant for the log Sobolev inequality, and using Gross's connection between log Sobolev and hyperconductivity. Okay. So luckily, all the hard work has been done before. You really know exactly how hyperconductivity behaves in the sphere. And I should say, what we're doing here is very similar to what was done, say, by Talleyrand and by KKL. They worked in the hypercube. They worked in 0, 1 to the n and used the hypercontractive inequality over the hypercube. But what we're doing here is almost line by line the same, just for the sphere. Okay, so what's demonstrated there is what the hyperconductivity is all about. Let me just say, in case you haven't seen this before, what it says for the sphere. It says that if you take any function of the sphere and apply a certain amount of time of the heat flow operator, I won't define it here, and what it says is the high norm of this operator, some norm q, is at most the 2 norm of the function f. So it just gives you some quantitative way to describe this phenomena that heat flow smoothest functions. Okay, this is what the hypercontractive inequality says. And you can see the demonstration, say, for the linear function, but any function you can do this. But one thing you can see in this linear function demonstration is that the linear function is an eigenfunction of the heat operator. See, I take a linear function, I don't know if you can see from the picture, it stays a linear function, it just kind of cools down, but it's still a linear function. And indeed, this is something we'll use, that the subspaces Sk are eigenspaces also, not just of the Rodon transform, but also of the heat flow. And that's for the same reason. That's because the heat flow commutes with the SON, with rotations. And again, you have to do some calculation. I won't do the whole calculation here. You compute the eigenvalues. The point is the following. The reason this is so useful, the hypercontractive inequality, is the following. Because if we have a polynomial of degree k, of spherical harmonics k, we know exactly how the hypercontractive inequality acts on it. It just multiplies by a scalar. Because a polynomial in the spherical harmonics is an eigenfunction of the heat flow. So we know that applying the heat flow to it just multiplies it by scalar, and just now by rearranging, I get an upper bound on the Q norm of the function in terms of its 2 norm. Okay, and this is, as we saw today in Rafa's talk, this immediately gives you tail bounds. Once you have bounds on the norms, you can get from this easily tail bound. But in this case, just a simple Markov inequality. Okay, so this concludes the proof. So what we do here, we just first use the Radon transform to bring it to nice analytical form, just in terms of the spherical harmonic decomposition, and then use the hypercontractive inequality to bound the mass indicator function can have on each level of the spherical harmonics.
So you need to use the relationship between C and Q, or somehow that's not important?
Yeah. So I don't give all the parameters here, but of course, yeah, you need to use the fact that, I mean, there's a function relating, so you need to optimize over Q essentially if you want to get a tail bound. Yeah. Yeah. I mean, P is an arbitrary polynomial, but you use as a function of K of the level you're in, you have to optimize Q to choose Q properly. I'm not doing this optimization here.
P and Q are
No, that's obvious.
Yeah, I know. I mean, you mean the two.
The hypercontractivity. You have to use the relationship between how far you flow and the...
Yes. I mean, you just have to plug in the right parameters. I'm not doing it here, but it's almost identical to what happens in hypercube. Okay, so let me just conclude with one open question. Actually, there are two, but the first one is more mathematical, the second one is more for CS. So the first one is we'd like to improve this to a tight, square root, and low bound. We kind of have a guess on how this might be done. It turns out this requires a stronger geometric sampling statement. I won't describe it here, but just if you're interested, I can tell you more about this offline. Essentially saying that if you have a subspace and an orthogonal subspace, then kind of together they do some reasonable sampling of the set. So maybe the subspace itself misses the set, but together with its orthogonal complement, you're doing pretty well. So I can describe this offline if anyone is interested. And one question for the CS audience. It's a big open question to get separation, any separation that's better than quadratic for total functions. So we have separations only for partial functions, like I showed you here. I mean, there's a promise on the inputs. They're not chosen from a product set. And this is a big open question. Not much is known there. It might even be impossible. So it might even be impossible to get strong separations there. Okay,
so is there some candidate where you have log n?
No, that's what I'm saying. So there's no candidate, but and actually you might conjecture that it's impossible. You might conjecture that they're always within some polynomial of each other. Okay, because
so this is you need some quantum work.
Yes. So to prove something like this, if it's indeed impossible, you will need some true quantum work. You will need to show that take any quantum communication protocol, how to convert it.
If you want to
to classical protocol.
A result like your result, then you need the algorithm, a protocol for more general functions.
Yeah. So if you want to prove a separation, like my result. So if you want to prove like that, so you would have to find some function, hope that the quantum protocol is not too difficult. Usually it's not, and then show lower bound classically. Yeah. But I think there's no good candidate. That's the problem, because once you have a candidate, at least you have some guess on the conjecture, but we don't have any good candidates here. It might even be impossible. Okay. So, thanks.
Any more questions?
Right.
Are there any obstructions to carrying out everything in Gaussian space rather than on the sphere?
Oh, yeah, good. So the question was about Gaussian space. Actually, I don't. So I think we wasted several months trying to get the statement in Gaussian space. I don't know of any way to phrase this in Gaussian space. So I can't say anything too precise, but it seems like the statement makes sense in the spherical setting, and it's very delicate. So the minute you try to transfer it into the Gaussian space, it breaks apart. It doesn't make much sense, and I can try maybe to convince you later. I'm not sure if it makes sense there.
Avi?
I'm just wondering if there's a relationship between this result about the sort of the inner product of two small sets using this application of the hypercontractive estimate, whether in the cube or in the sphere. And another paper of yours, which I guess with Benny Sudakov and with others, in which you talk about the length of path between small sets, let's say on the hypercube, using the Beckner also. So is there a relationship between them?
That was reverse, but
Yeah, so that was using the reverse hypercontractive inequality, and the statement was a bit different. They want to, I think, you want to low bound how small can be the correlation between two faraway sets. Yeah, I think here's a different setting. Here you're in a setting where things smooth, so you actually. So I think it's a different setting. I think that was actually the other side of the spectrum. And yeah, I mean it's okay. I can try to answer this maybe later, but
More questions? Okay, thank you again.